Hi there, let's take a look at physics today. We're looking at lesson one on acceleration. This is from your textbook on pages 57 through about 65 or so. And we did this over the course of 2 days, both Thursday and Friday. Before we jump into a little recap on today's activity and even tomorrow's, just back up a few pages in your textbook, just to give you a few little notes here, things that came up a little bit, maybe some of your questions as well that you might have had that were probably in previous lessons that we didn't do this year. So first of all, some pre-acceleration notes. First of all, we're going to talk a little bit about things that are called vectors. You'll see that word tossed in there oftentimes. A vector is a quantity that has both size, which is like magnitude, and direction. So when we start talking about vectors, we're talking about a quantity that has both size and and direction. We'll also take a look at the what's sometimes called the delta or the change in time, which is a time interval. So look for this type of symbol as well. One thing that we looked at and we kind of had a hunch about, and sure enough, it was there. When you see that little I or the F on some of these equations, the I stands for the initial and F stands for the final when you're talking about different values. So you'll see that here, for example, right there in this little equation for the average velocity, you can see the F and the I for the final and the initial. So when you're comparing something and trying to find the difference, you're looking at doing the final and then subtracting the initial value there. And that's something you use to find, for example, the average velocity. So our average velocity here is going to be found by finding the difference between the ending point and the initial point divided by the time from ending to the initial point there. So that's a little equation you might use from time to time. Displacement. Displacement is the change in position from initial to final. So it's being displaced. It's like moving. So the change in position has to do with being moved. That's displacement. So that's why it's an x of the final minus x of the initial. That's the amount of change that's happened from this one to that one. And finally, the term position comes up. An object's position is equal to the average velocity, this one, multiplied by time plus the initial position. So if I want to find out an object's position, this is an equation that I could use to find an object's position. So I just make note of those because they came in prior lessons to today's, and you might need to use them in future things. Not positive yet, but you might. So here's a take a quick look at my notes from today's lesson in reading through these first pages. The first part was on non-uniform motion diagrams, and it began with this little drawing here. We had some people running here, and you had a person, first of all, a person just kind of sitting still, but then you had people that were kind of like in the same distance across, kind of running. And that was really showing us really what was we call constant velocity. And so a constant velocity happens when these arrows, velocity indicators here, are the same length. That's going to be a constant velocity. When the arrows go from kind of small to a little larger to even longer, what's happening there is it's demonstrating something that is speeding up. All right, because it's getting longer, it's going faster, speeding up. When, however, the arrows tend to decrease in size like here, we would say that what's going on is it is slowing down. And this is using what's called a particle model. In a particle model, what's taking place is the dots represent the changes in velocity, and the arrows represent what are called the velocity vectors. In the get it question, it asked you, I think let's see if I get it here. The get it question is what do increasing and decreasing lengths of velocity vectors indicate on a motion diagram? All right, so on a motion diagram or a particle model, the increasing length is telling you that it's speeding up, and a decreasing length tells you that something is slowing down. So in this case here, if we look back over here, this is slowing down because it's getting less space from dot to dot, whereas here we're definitely speeding up. So that was part of that kind of topic there. The other thing that came up in there was what was called the acceleration, and acceleration is the rate at which an object's velocity changes. And it went through a little three kind of step process to show you how that works. So let's take a look at this together real quick because I do think it's important. if I do a blue square around this particle model here, we can see already that it's definitely like speeding up as we go along, that's for sure. But I'm going to call this velocity vector my velocity, my final, and this one my initial. And what I'm going to do is use these two to draw a little picture to kind of compare how we could look at those to find what the acceleration is going to be, the acceleration rate is going to be between those two velocity vectors. To do that, what we do is we take the final one. Remember well, we don't have it quite down yet. We're going to take our final one. We have to find our average velocity rate. Now, the average velocity is going to be here, and you're going to take your velocity of your final minus your velocity of your initial. Now, our velocity of our final one is this length right here. So I'm going to draw that length out real quick. Draw like so. So it's about the same length as that one. That's our velocity one, our velocity initial. Yay, there, our velocity final, sorry, velocity final. And then you take from the head of the one or the where you started at, and then we do our velocity initial going the opposite direction. So my velocity initial maybe is about this long. So we have a difference here between our velocity final and our velocity initial because one tends to be a little longer than the other. But then we have this difference here for this space, right? We have this little funky little space right here. Get a different color here for what happens in this. Okay. Well, that area is what we're going to use as really that is our change in velocity or difference in velocity is that space there. The difference in velocity, though, becomes our acceleration because acceleration is going to be equal to the change of velocity divided by the change in time. So in this case here, our change in velocity divided by change in time, the difference is we have, and we used a purple one in our notes, if I remember correctly here, purple. It's going to be this space right there, and that change becomes our acceleration vector. Okay, that's our A value right there. That stands for the acceleration amount, acceleration there. Now I'm going to have it go the same direction as whichever value was larger. That's what I tend to notice so far. So for example, the final vector is the larger one, and so we're going to keep our acceleration going the same direction because almost like it has more left over, so to speak. Kind of a simple way of thinking of it like that. But we'll do some more examples here in just a moment. So that's that first part. We move on from there into the direction of acceleration. And they gave you a picture in figure 4 on page 59, of four cars, two going towards the right and then two going towards the left, and one kind of heading towards the stop sign and one driving away. So anyways, different pictures. But I drew our vector models here because I wanted to like just kind of work with these with you for just a second to see how do we figure out what the acceleration is going to be. So again, what we're going to do is we're going to decide what is our final and our initial. And for this case here, what we'll do is I'm going to make this one my final, vector final, and this one my initial. So using the same kind of pattern I did before, I'm going to do my final one, which is going in this direction, that length there. My initial one is this one going back the other direction, but less space. And so what I'm left with then at that point is I do have this little space right here. And I know that there's more on the top than there's bottoms. My arrow would go there, so to speak. And so for me, I would say that my acceleration arrow is going to be this much going in that direction. That becomes my acceleration based upon the fact that this space right here is my change in velocity. So that change becomes my acceleration, and that's what we have there. Now, it's going to be yeah, so we're going to just leave it like that. So that's kind of how that one works, all right? So we know we have a positive acceleration in this picture, the diagram, and a positive velocity. And so when we have a positive velocity and a positive acceleration, they're going in the same direction, it's going to be actually speeding up. And so in this case here, we can see based upon the particle model that indeed the car is getting faster because both of the arrows here are going in the same direction, so it's speeding up. When I look at the next one, I notice that my acceleration and velocity arrows are going in opposite directions. So because they're going in opposite directions, we're going to assume it's probably going to be slowing down. We look at the dots and we notice that they're getting closer together the closer we get to the ending point. So indeed, this car seems to be slowing down or decelerating. So if I, once again, make my velocity one, this one here, and my velocity final, this one here, and then draw my arrows, let's do the velocity final first. Velocity final this time is going to be a little shorter, right? Whoops, than the velocity final. So there's my velocity final. And now when I do my velocity initial, I start here, I'm going to go back this direction. It's going to be longer. Now, because it's longer, that means that my change in velocity is this space right there. And so it's going to go in the direction of whatever one tends to be longer. So my acceleration arrow in this case is going to go from here to here. And that's my acceleration arrow there, demonstrating what the acceleration is, which way it's going, and how that works. So this one shows me that it's slowing down because they're going in the different directions. So if I have opposite directions, it's slowing down. When I have the same directions, it tends to be speeding up. We'll take a look at the next one real quick. So let's label it once again. We're going to label this as our velocity beginnings here. So got to pay attention to this here, beginnings here. So we'll make this our velocity one and this our velocity two. So then I get my arrow out and, oh, sorry, velocity one, two. So sorry, velocity I and velocity final. Okay, so now we do our final one first, which since is going this direction. There's my final. And so we're going to go this way to there. And then I bring back our velocity initial. It tends to be a little shorter, so it goes there. So what I'm left with then is this space right here. Right, good so far. Now, because that space right there happens to be, well, actually, it wants me to do it a different way. Let me go to, I'm going to do it the way the books can't tell me to do it. I'm going to change this little line here real quick. Oops. I'm going to change my velocity initial to go, they like to go this way, which is fine. And by doing that, that means that what's left is my acceleration, which is this piece right here. So my acceleration is going to be this little chunk going in that direction. Now, once again, we can see that both arrows are pointing the same direction. Because they're going the same direction, that means this car is speeding up going towards the left. And then when we look at our last one, we have our initial and we have our final. In this case here, our final is going to be the short one. And our final one comes off of that one and it goes this direction and it's going to be longer. And because it's longer, we see what's left is going to be this space there. So our acceleration is going to be what's left here. And it's there. Now it's going opposite directions. Right, opposite directions. No, actually, it's going the same. Yeah, opposite directions. So we're good. Opposite directions, and that's why it's slowing down, going the other way. All right, so we got that there. Great. So that was kind of my notes from that part there. Velocity time graph. Now we're going to kind of run through some of these here. When it comes to the velocity time graph, what we're looking at here is kind of going back to slope. Slope has to deal with the rise over the run, how much something goes up and down, divided by how much it goes kind of left and right. And so in this little graph that it gave you in the book, it was talking about velocity and time and gave you an example here for a velocity and time graph. We're looking at how much something goes up and then how much it goes over. That's the rise and the run. So in this one, we have a graph of a car starting and accelerating at a constant rate. The rate of change is the slope. And so the rate of change in this case here happens to be 5 over 1, or just simply 5, because where the velocity is going up 5 and it's going doing that in 1 second. So that's my rate of change is 5 and 1. I can see again when I look at the next point, I'm going to go from 5 to 10. So that's also an increase of 5. And from 1 to 2 is an increase of 1. So I see the same slope. It's a constant rate at that point. So whatever is happening with this car, it's accelerating at a constant rate. It's staying the same. It's increasing 5 meters per second every second. So every time we go a new second, it's going to go 5 meters a second faster than it was before. And that's that constant velocity. And that's what we see there. It should be a nice straight line. It's not always a constant velocity as we see later on, but this is one that is a constant velocity. The other graph that it gave you here was looking at the runner's motion graph. Now, this one's a little trickier because when you start talking about motion, you're talking about where an object is in like position to like space, like where does it exist? So this is where things do start to get a little more complicated. So in this graph here, we first of all, they decided to call east kind of positive and west negative. Not for any reason, but just to kind of help you kind of orient yourself. So I put a plus here and a minus there to help me know that I'm moving in a positive direction when I'm going east, and I'm moving in a negative direction when I'm going west. A little bit like thinking like, when you're doing math and you're graphing, you have a coordinate plane, positive, negative, like that as well. Okay, so we have really several different red lines here that are on this same motion graph. We have the red line for A and E, both of which are a horizontal line, which means when we look at these guys, their slope, it's not going up, it's not going across, it's the same, it's a constant. There's no slope there. And so because the slope equals 0, we would say in this case here that there's no acceleration and it has a constant velocity. So what that means if this is a runner, that means the runner is going east, it's in that direction, right? There's no change there, but it's not accelerating, it's going the same rate the whole time, and it's a constant velocity going the same pace the whole time. This one here, but they just happen to be going towards the west. So going a different direction, but there's still no acceleration. They're both going different at a constant velocity. They're a different place in terms of their motion and where the direction they're going, but they have no slope, no acceleration, constant velocity. When you look at runner B is starting here what we would kind of call the origin and seems to be going towards the east, right? He's moving more in the positive direction there. So we would say that he has a positive velocity because he's moving towards the east and also has a positive acceleration. Now, the reason we would say he has a positive acceleration is because he has a positive slope. And it's a positive slope because why? Well, it's going up. We see a constant increase going here. The rise over the run, it's definitely going in an upwards type of direction. And that's, of course, opposite than the C runner, which we can see the C runner starts off, begins with a positive velocity. It's up here, right? In terms of velocity being positive minus. So it starts with a positive velocity in the east, but because it's going down, we can say that it slows down. That's because of the slope that we see there being negative and eventually stops. Reason we say it stops is because it gets this point here at, we're between the east and west where the line just ends. So it eventually just stops there for whatever reason. That's the end of its motion. So it starts positive, it's slowing down, and then it stops. That's the runner. Now, runner D is a little interesting because it starts in motion in the west. So it starts in the west, or what we would kind of say the negative side of the graph. Okay. So it starts down here. And because it's going towards the origin, so to speak, we're going to say it slows down. So it's slowing down at that point there. And then for a moment, in an instant, it has no velocity at all. And we can say that because at this point right here, when it hits the middle point, it's not going east or west. And so for a moment, it doesn't have any velocity. And then it increases its speed and moves east or positive. So a couple different things are happening with each of these, but just ways of analyzing the different graphs and how, whoops, how the motion works there. Okay. So that's a little bit from today's activity, today's reading for what we did in class today. I'm going to pause there and then we'll pick up with what we're doing tomorrow in just a moment. See you next time.